So move to your point around here.
Yeah, good.
Then option is
And
come
it
down.
comes down. Yeah,
Yeah.
good. Okay.
Professor Scully?
Hello? Yeah.
Hi. Are you listening to us?
Yes.
Yeah, I don't have very good audio, but good morning.
Good morning. For us, it's already good afternoon. I will
After-
remove the mask so people
Yeah.
can hear me better. So hi, good afternoon, everyone. So welcome to this next section of our school. So I will be the chair of this section. And we have as our first speaker, Professor Marlon Scully, that is already with us via Google Meet. We are all seeing you on our projector, Professor. So I will just do a very brief introduction of Professor Scully. So Professor Scully has a long-standing career in physics with seminal contributions to laser science and quantum optics, including the Scully-Lamb quantum theory of the laser and the classical theory of the free electron laser. He has been a faculty at Yale, MIT, University of Arizona, University of New Mexico, and at the Max Planck Institute. At the moment, he holds appointments at Texas A&M, Baylor, and Princeton universities. Today, he will present his first lecture to the school, titled "Of Bose Condensates, Squeezed Light, and Black Holes." So thank you very much, Professor Scully, for joining us at this school. And as we are doing a hybrid school, we have some participants here with us presentially, and we have some people also watching you via the YouTube channel. So after your class, we will open to questions, and we will have questions from the audience here, and also questions done online. So I just ask some patience because I will have to try to deal with both channels of questions, okay? But we can organize. Okay, so thank you very much. You can start whenever you want. Thank you.
Good morning. It's a pleasure to be here. The Brazilian scientific reputation is, of course, excellent, and it's an honor to be included in your school. I am speaking about the application of quantum optical techniques to problems in Bose-Einstein condensation, including Bose-Einstein condensation with interactions. And in that context, I make use of the Bogolubov transformations as they're listed here. In view of the world situation today, it's appropriate to remind ourselves that Bogolubov, famous theoretical physicist, has an auspicious name. His name means "I love God." His father was a Greek Orthodox priest. His grandfather, as I understand it, was Jewish, and the family was a religious family. He himself was a believer. He went to school in Kiev, got his PhD in Kiev, and was a very key figure in organizing what has come to be known as the Kiev School of Theoretical Physics. Started off as the Kiev School of Nonlinear Mechanical Research. He wrote famous books on the subject, and of course is a super decorated physicist. In terms of what, let's see, what are we? I'm trying to use my computer here in new ways, so you'll bear with me. So the talk that we're going to be focusing on today is the use of quantum optics to better understand certain aspects of Bose condensation. In particular, we'll talk about the, excuse me, we have dust around here. We have a series of tools coming from the interplay between optical and statistical physics, which we'll be discussing and using today. First, the Bose-Einstein condensate and the Uhlenbeck-Einstein dilemma. Then the emphasis of my talk is fluctuations. Why study fluctuations? And we'll go over that. And the quantum theory of the laser is indeed dominated by this question. Questions of the photons. Statistic. I apologize, bear with me. The atom laser, the Bose-Einstein condensate. And then in 4, talking about the interaction of atom interactions and the Bogolubov transformations that were so famous in the study of superfluid helium. Remember, Landau made his famous quote, which bears remembering. And Landau says, and his famous statistical mechanics book, the fundamental properties of the Bose-Einstein gas have not much to do with superfluidity. Let's see if I can find. Then he goes on to say that it was Bogolubov who was the first to derive a consistent microscopic analysis picture of quantum liquids in this regard. And the application of these Bogolubov quasiparticles to our problem lead to many open questions. And I'm looking always for students and postdocs. So I hope to entice you with some of these questions, because there's a lot of interesting physics here, and we don't have time really to get into it. Now, remember our BEC hero, Dan Kleppner, and I should confess that back in the day, when Dan Kleppner was talking about Bose-Einstein statistics as something that we might be able to study in Bose-Einstein condensates using lasers and cooling the atomic gases, I didn't believe, because I thought that, well, when you cool these molecules like rubidium or even, please, hydrogen, that it would cause a condensation and you'd get small little snowflakes, not a Bose condensate. But of course, as we learned later, the issue of Bose condensation and the characteristics of a bound system, like unto 0-point fluctuations, are very essential in understanding this problem. And it's that part of the physics that we were missing, I was missing. And of course, Dan's prediction came true. So he's the real hero. And at one point, he noted that this Bose condensate was like an atom laser. And there, if that's true, I might say, well, if the laser is characterized by photon statistics, which are, by the way, not Bosonian and certainly not Boltzmann thermal, what is the atomic distribution, the characteristic of the atom laser, Bose condensate? We'll get on to that. And so when Dan published his famous Physics Today article, which I just showed you a picture of, we ask ourselves, many of us, is the Bose condensate an atom laser? And I say the strongest argument in favor of that is that Dan Kleppner says it's so. But Willis Lamb and I both said probably not, because here is a paragraph from a later article. It's the nonlinearity that is essential in describing the laser and the quantum theory of the laser. And now you say in the Bose condensate, what's this nonlinearity? Is it due to atom-atom scattering? Or is there a nonlinearity even in the case of the ideal Bose gas? Turns out that the latter is the case, and that we're going to show over and over again. But before we get into that, let's review the issue of Bose condensate, fluctuations, and some of the early debates that took place between Einstein and his colleagues. So you remember that for a thermal gas in which the Bose-Einstein statistics describe the atom. So we have beta 1 over kT and the energy of the atom, and mu, the chemical potential. Now here we're, of course, in the grand canonical ensemble, and this is an important tool in statistical mechanics, because when you start trying to solve for the partition function in an ensemble with fixed number of particles, the canonical ensemble, you've got a hard problem. But if instead of fixing the temperature and the number of atoms in your gas, as we do in the canonical ensemble, we fix the temperature and the chemical potential, as we do in the grand canonical, then things become much easier. So let's focus for a few minutes on the grand canonical approach to the problem, because that's what Einstein and everybody else were using. Let's set the velocity of the atom equal to 0. Let's call the average number of atoms in this ground state in 0 bar. And in particular, then, if this is in 0, we can solve for the chemical potential, and we get this expression for the fugacity, if you will, for the chemical potential, in fact. And we get now the equation for the number of atoms in the gas, in which we can sum over all states, and the ground state included. And when we do that, we find that, look, just as you well know, the total number minus the average number in the ground state is equal to the sum over the atoms in the system that we're investigating. And in particular, here, Einstein has set mu, the chemical potential, equal to 0. Not a bad approximation if you look at it back here, right? N0 is some big number. So mu is essentially 0. This fugacity is 1. Solve for the total number. Now, if I'm summing from k equal to 0, I have to separate off that first term, because if this is 0, then I have 1 minus 1. Well, well-known story, but this is what we end up with, right? This is the key expression for a Bose condensate. And now, if I go to the critical point in which n is equal to n0, I can solve this expression for the number of particles and the temperature related to the total number of particles, okay? So I set n0 equal to 0, and I solve this equation as indicated, and I should have a beta sub c here. This is the sort of thing that I'm thinking about. I'll come back to that in a moment. So when I'm pulling all this together, solving for the temperature T sub c in terms of this expression, we get this well-known result. Okay, so we all know that. This isn't quite what Einstein did. He was looking at particles in a box, and so the exponent was T over Tc to the 3 halves. And for a harmonic trap, it's cubed. And so Einstein then found a cusp at the temperature Tc, and that prompted people to ask lots of questions, like Uhlenbeck. George Uhlenbeck, a hero in my day, maybe not so well known to people from the quantum optical persuasion these days, but great hero in statistical mechanics, a student of Ehrenfest. I had the good fortune to study theoretical physics from a student of Uhlenbeck's, Professor Bob Bessey. And so I always enjoy and appreciate Uhlenbeck's teaching. And by the way, let me mention again, as I will mention again, that his student, Boris Kahn, figures in these discussions. He was killed by the Nazis as a Jew. Uhlenbeck up here points out that there is this cusp, and he thought that that meant Einstein was wrong, because you don't have discontinuities in theoretical physics. Must be some sort of way in which this cusp is to be understood, and not that it's a really essential part of the physics. And he points out that Ehrenfest thought that was true. He wrote a letter to Einstein, and he said something like, when the masters fall or the masters fail, the young people have to do some work. And Einstein, as Uhlenbeck says, agreed with the criticism. And Einstein thought that the problem was replacing sums by integrals. But that's not true, actually. You can do the sums exactly for the harmonic potential, and you still get the discontinuity. So let's move on. But there's this interesting little poem here. The issue was that when the kings are building the sewer cleaners, the rest of us have work to do. But that isn't really true. Einstein appreciated the jokes, but he wasn't convinced. And in some sense, it is the case that the problem comes from placing the chemical potential equal to 0. If you go back and keep the chemical potential, that is to say, keep this bracketed expression in the denominator, Okay, now you have an equation for n0, and you can easily rewrite that so that it is a quadratic equation for n0. And you see that the result is this red curve. That's what you get when you do the problem more carefully. It's still the grand canonical ensemble, but you don't make the same mistake in this in the thermodynamic limit where there's a cusp. You have this kind of ubiquitous result, and we can solve the ideal gas equations on the computer, of course, and that's what the dots are. So the grand canonical and canonical results are the same, essentially, and this an error, but that's because you've made the approximation as mentioned. Now, let me remind you that if you solve for fluctuations in the grand canonical ensemble, you get this crazy answer, which people have called the grand canonical catastrophe. Interesting. And indeed, one must be very careful when calculating fluctuations. And our hero Terhar, back in the 70s, by the way, Terhar was the thesis advisor of Tony Leggett, and quantum optical Leggett got the Nobel Prize for helium-3, and also Terhar was the thesis advisor of Stig Stenholm, quantum optics hero. But his logic led to the wrong equations. The ordinary grand canonical results give you an infinite result here at low temperatures. Terhar gets the fluctuations going to zero for low temperatures correctly, but as he goes toward TC, his calculations go wrong. So, as you find in elementary StatMech books, it's very inconvenient to work in the canonical representation, as Cattell tells us. And in the early days of thinking about these problems, or maybe I should say rethinking these problems, the statement was made in PhysRev that there is no simple analytical expression for the partition function in the canonical representation in 3D trap. Well, that's not true anymore, but we were glad to find this quote because one of the things we get is a sum on states very readily. So we're going to be looking at fluctuations. Should we study fluctuations? One of my humorous colleagues, brilliant physicist, said, no, because when you're done with your work, all you have are fluctuations. You should look for the average value and forget the fluctuations. But I say yes. Remember that Einstein was studying the fluctuations of light. when he came to the wave-particle duality and got the Nobel Prize for it. The Nobel Prize, as you know, was given for the concept of the photon, not for relativity, as some people think. Let's remind ourselves of what Einstein and Planck were doing and how Einstein turned simple considerations into a deep insight. So you remember that Wien was famous for making this statement about the energy plotted versus temperature for our system of interest. And he then led Planck to consider the question of the entropy of light described by this energy function. And by the way, Planck said that he was not very patient with people who wanted a career in physics. He never wanted a career in physics. He just wanted to understand the second law a little better. Indeed, he did. He tried other forms of this vile entropy, okay, and got the temperature, the derivative of the entropy with respect to the energy, such, turned that around, solved for the energy density, and got something which is the famous Planck distribution. Einstein then said, well, look, S equals K log W from Boltzmann, and let's just then solve for P and put in an expansion for S. And we've got from Planck that this expression has a simple analytical form, and we can then solve for fluctuations of energy in this way. The energy minus the average energy, looking at the variance in the second moment, gives him two terms. He gets a wave-like contribution and a particle-like contribution to the fluctuations. And this was wave-particle duality. This was the birth of the photon. Now, in his famous 1905 article, he says that this doesn't violate the photoelectric effect, but it wasn't the photoelectric effect that he was using as the basis for his beautiful deductions. It was fluctuations. Now, let's talk about the quantum theory of the laser, and in particular, look toward the question of fluctuations in both condensates and the atom laser. I was lucky as a student to work with Willis Lamb, who in the times when I first met him was only half a dozen years away from his famous Nobel Prize in his work for the Lamb shift, his work in explaining the structure of the vacuum, so to speak, making quantum electrodynamics a respectable subject. And then came, well, he did that, by the way, at Columbia back in, 47. And he was still an assistant professor at Columbia. He got his PhD in Stanford with Oppenheimer. And then Robbie was looking for a brilliant physicist, and Oppenheimer recommended Willis. So Robbie drove out to Berkeley from Columbia and picked up Lamb and brought him back to Columbia, where he then from that point on did many things. He for example, was the first to derive the Mossbauer effect, or recoilless emission, called by people who are in the know the Lamb-Mossbauer effect. Never published with Oppenheimer, didn't really get along with some aspects of Oppenheimer's personality. For example, he told that one day he was riding in a car with Oppenheimer around, let's say, 38, and he said to Oppenheimer, when the war comes, and Oppenheimer, of course, being a product of Goodingham and Europe, said, there isn't going to be any war, you damn fool. Well, Lamb was a very excellent physicist and thesis advisor. For example, student goes into him and says, Professor Lamb, I'd like to work for you. Lamb said, well, I don't take first-year graduate students. Student says, well, I have special qualifications. And Lamb said, oh, well, then I would be interested because I have so few qualifications myself. So it was my good fortune to work with Lamb and developing the quantum theory of the laser, developing a technique which could be applied to many other subjects, like the theory of Josephson radiation. Patrick Lee, who went on to do beautiful things in solid state physics and other areas, winner of the Dirac Prize, a solid state physicist, head of the MIT condensed matter group for 20 years, uses these techniques in his thesis to calculate the line width of Josephson radiation. Towns and Schleich, of course, everybody knows Towns, but you might not know that he was a very insightful, essentially theoretical physicist. He tells that when he was a graduate student at Caltech, he couldn't consider a problem in theoretical physics because he worried about his eyesight. So he went to experimental physics, but he had deep insights. We'll get to that. Wolfgang Schleich, my first student in Germany, just won the Herbert Walter Prize, and by the way, brought in €1 billion for study of quantum mechanics and quantum computing. So back to the fluctuation issue in lasers and to Towns. Shimoda, Takahashi, and Towns were amongst the first to study and think about the question of fluctuations. Towns was trying to understand the line width of lasers better. Remember that the line width of the laser and the maser is much, much narrower than the characteristic line widths of the photon, say, in a cavity. The photon has a line width in a Fabry-Perot cavity, which is on the order of megahertz. The line width of the laser is on the order of a few hertz. How can this be? When Towns tells it that when he explained this to Bohr, Niels Bohr, Bohr didn't believe it. And when he explained it to von Neumann, initially von Neumann didn't believe it, but then came back and said, okay, you're right. So how do you calculate this line width in a simple way? Well, Towns, his graduate student, Jim Gordon, and his brother-in-law, Art Schellow, calculated the line width and made contributions to our understanding of this fundamental aspect of theoretical physics in many ways. Here's one way. Ask, what's the probability of having n photons in the cavity? That's P of n. P sub n, the photon statistical distribution of light in a single mode cavity. write that equation as you might have been wont to do in 1957 for a maser, in which the gain alpha contributes to this piece of n expression by gain which is stimulated and spontaneous. If you start with n photons in the cavity, you will lose that piece of n by a little bit, and that's the origin of the minus sign. If you have n minus 1 photons in the cavity and you emit 1 due to gain, then you increase the time derivative of this distribution. So this is the gain contribution to this flow of probability. There's a loss term. Gamma is, say, nu over q of the cavity. So if you start with n and lose a photon, that's a minus contribution. If you start with n plus 1 and a photon leaks out of the cavity or is lost, you add. Now, I mention that to you because it's an easy equation to solve. And when you do solve it, you get essentially single mode black body radiation. And indeed, if you go back to look at the result that comes from, say, a klystron or an oscillating ensemble of charges, you get something which is a Poisson distribution, as Glauber taught us. Here, that should be about 63. And Glauber makes the interesting observation, brilliant physicist that he was, he understood that the nonlinearity was important in getting the right description of laser radiation. And then Lamb and I worked on the problem from the point of view of having a cavity, two mirrors, model in which there's a single mode in the cavity. We have atoms, so let's just think of them as being in the excited state, and we have, say, phonons in the mirror, which are as if we have a system with everybody in the ground state. You can solve that problem and find that you get something for the photon statistical distribution, which looks a lot like what Shimoda, Takahashi, and Towns had. By the way, I didn't know about that famous paper back in the early 60s when I was working with Lamb on this problem. Indeed, the Shimoda, Takahashi, Towns paper misses all the off-diagonal elements. It gets the diagonal elements about right, but not the off-diagonal terms. And those are the terms that we must look at for calculating fluctuations in the line width. So alpha is a linear gain. Beta, that's a nonlinear saturation parameter associated with the fact that an atom in the excited state decays, and now it's an absorber. And that subtracts from alpha. Well, this we know, and we can solve that equation at steady state. I'll put this term equal to 0, solve, and get an expression for the photon statistic to the laser. Now, the reason I'm going through all this in detail is you can see why Lamb and I were dubious about the atom laser designation in physics, because here's the statistical distribution that you get. It's a product over the discrete numbers k, which are like photon numbers, and n is a normalization factor. If you plot out this distribution, you get something that when you're near threshold, and that's where we're interested, right? Way up here, Glauber was right. Way down here, Shimoda, Takahashi, and Towns are right. But the interesting region is the threshold region. And there, the distribution, it turns out, is orders of magnitude narrower, say a factor of 10 to 100 narrower than a Poisson distribution. So this nonlinearity is essential. Now, before getting back into the Bose condensate business, let me return to the question of the quantum theory and ask, what about the off-diagonal elements? So we were always talking now about the equation of motion in which K, the degree of off-diagonality, is equal to 0. Then you get coupling like that along the diagonal. Fair enough. Now, when I go off diagonal, oh, interesting. Now I still get stripe coupling. Rho n prime, that is to say K not equal to 0, couples to the same K value. And it turns out that when you solve for this total density matrix, these terms decay. And so this is all that's left for long times. But when you're looking at the line width and higher order correlation functions, you must consider these off-diagonal elements. That's a non-trivial problem. And we considered the problem theoretically and found that for a electric field equation of motion, that for the creation operator, negative frequency part of the field operator, you have a time dependence governed by the density matrix, density operator that we had in the previous view graph. You solve that problem and you find that the off-diagonal terms decay away in something which is very close to what Towns and co-workers were thinking. And if I had a little more time, I'd like to develop that with you. But what we started looking at, for reasons that I won't go into right now, recently, is the question of first order correlation, K equals 1, line width, second order correlation. People don't look at second order correlations typically in the case of the laser. This is likened to the Henbury-Brown twist correlations, G2 in Glauber's notation, but it's not G2. We're talking about this density matrix time dependence. Go to third order. And what you're finding always is that these widths, the width of the laser radiation is indeed something which is going like the degree of off-diagonality squared. So let's see, let's finish this part of the discussion by mentioning that the concept of off-diagonal order is something which Yang and co-workers introduced in the concept of superfluid helium, in the context of superfluid helium. And there's much in common here with the physics of those kinds of problems. Now, with an eye on the clock, let me jump ahead to the atom laser problem. And again, we note, I hope someplace here, we're asking the same question that we asked for the laser. What about the nonlinearities? And here we say in the abstract of this paper, the n particle constraint plays an important role in this nonlinearity. So the thing we called beta earlier, now it comes in because we're working in the canonical ensemble. That's very interesting and fun. And what I was doing in this problem, and even though I'm running out of time, I'm going to take a minute and explain this. The problem of superfluidity really began in a time which was much before the laser cooled gas era. This should say 1985. John Reppy, my teacher at Yale, did some beautiful experiments at Cornell in terms of using a porous glass, a glass that had pores in it like a sponge. And he would put this porous glass in liquid helium, cool it down, and then when the liquid helium became superfluid, the superfluid material would leak into the pores of this sponge-like system. And then atoms, which are in these pores and the little hollow ducts, so to speak, are protecting the atoms from collisions with the walls because of superfluid behavior. So you get individual atoms displaying essentially independent atom Bose condensation. So think of the Vicor glass as just providing a mechanism for loading a system at, I don't know, 0.1 or 0.01 degrees Kelvin with Bose-Einstein particles, and then doing the measurements that they did so beautifully. Well, let's then imagine that we've got a trap which holds these atoms, and for the rubidium traps that the laser gas heroes use, the problem can be thought of as having parabolic traps. But for what we're going to do today, let me just think of a trap like Einstein had, for the most part, a box with walls, okay? And in that regard, then I will take interactions between the atoms with creation of particles in the ground state, say, and annihilation of atoms in the excited state with the corresponding subsequent simultaneous emission of phonons into the walls, some coupling constant G and a sum over the phonon wave vector and the atomic index K. So we now go back, do a careful, semi-careful analysis, making reasonable approximations. And what do we find? We find exactly the laser equations of motion, hot dog. So Lem and I were very interested in this problem. And of course, by that time, I was many years gone from working with him. I had the good fortune to lure him to Arizona, or we lured each other to Arizona in some sense. And we were still in contact, and he wanted that I would do the quantum theory showing that without atom-atom interactions, no nonlinearities, and no way of getting this kind of master equation. So I tried, and the opposite happened. If you notice here, the structure of these equations is a gain-like term associated with an atom falling into the ground state, and loss terms. This quantity H goes like is governed by the critical temperature, and it's a heating term. Kappa is a coupling between the walls and the atoms. And let's take that off the table for a moment. And so here we have something which has linear contributions and nonlinear contributions. And the statistical characterization of the atoms in the ground state exactly the same as the problem for photons in a laser. So the gain goes like kappa times n plus 1. Remember that n is the total number of atoms. The saturation then comes from the constraint, comes from the fact that n0 is upper bounded by the total number of atoms in the box. And the heating coefficient comes from a analysis of the problem, just tracking through the contributions. So that we can now calculate the atom average number and the variance. And what do we get for the variance? Something which looks like this CNB2. We did several of these coherent, N boson problems, not coherent, but condensate with N bosons, okay? So we had half a dozen of these papers. First and second of these papers gave us something which agreed almost exactly with numerical calculations. And then 20 years later, people's experimental heroes are doing these beautiful experiments in which they're actually able to get the variance expression. And I would love to go back and spend time looking at the interface between these calculations and this kind of experiment. And this is the place to look. So we're excited again about what they've done. But let's introduce atomic interactions, okay? So far, we've been thinking about the ideal Bose gas, but Vitaly Kocharovsky and his brother, Volodya, twin brother, were heroes in this business of many-body theory. And I was fortunate enough to have these guys as my friends and colleagues. And I kept bugging them, what can we do to include atom-atom interactions? And so the story then develops with an eye on the clock. I'll just sketch it for you and encourage you to look back at this work with Kocharovsky and Scully back in the 2000, 2001 Fizerov letters. And what we do is to use the usual Bogolubov operators. I say usual in the sense that you find this in Landau and Lifshitz. And in fact, by the way, it's still the best, most pedagogical treatment. And it's on page 98 of the book. And it is applied by our friends here. Sorry. And what they do and apply these Bogolubov quasi-particles to the problem of first looking at the average value and then calculating the fluctuations in a careful way. And when they do, they find that, hey, for an ideal gas of particles in a box, 3D box, I get a variance that looks like that. For the interacting gas, it's half. Take this squared. It's half of what you get for the ideal gas. And that's amazing. And they make the point that this is interesting. And then they say that the apparent similar behavior in the ideal and interacting gas is accidental. And we, in our work, were motivated by and had the good fortune to live in the same department as Dick Arnowit. And Marvin Gerardo was Arnowit's student back in the days when they were all in upstate New York. And we were able to do the calculation a little differently. And we found that we get strong pairing, so that when we calculate the squared variance of the condensate fluctuations, the interacting gas gives us 1/2 the number of quasi-particles as the ideal gas, so that the fluctuations in the ideal versus interacting gas, the one factor of 1/2 is not an accident. And in both cases, see if I can come here to something that shows, well, yeah, okay, here, running out of time, but note that here is the ideal for the average value, the ideal expression. And here is the number of particles in the ground state for the interacting gas. The scattering length A here, 0, and here it's some value. And we see that there are more particles in the ground state. We get a stronger condensation when we include particle interactions. Isn't that interesting? And now when we go back and look at fluctuations using this formalism that we developed, we'll find that the fluctuation variance expression gives us a good answer for low values, but applying this formalism that we see in the previous few graphs, when you get near the critical point, it goes wrong. And so that is motivation for looking at the question, how do I use these beautiful results, CNB3, and I say beautiful results, Vitali and his brother did these calculations that I had the good fortune to be associated with, and got good results for low temperatures for the variance. Something good down here, but up there it goes wrong. Well, Anatoly Shvydzinski and I had been working on this problem, again, from the point of view of using master equations and trying to take the ground state expressions. Let's quickly go a little bit further ahead. Now we're looking at a master equation analysis of particles in a box. And so here we get a good expression for the variance for an ideal gas, and here's the variance for an interacting gas. So that's kind of interesting, kind of fun. And you see then that by doing a phenomenological coupling of the average value and the variance for low temperatures, we can determine the coefficients for gain and loss, for increase and decrease of atoms in the condensate. And when we do that, we end up with let's go back, with these expressions for interacting particles in a box. And we have, for the different moments, the variance is, of course, the second moment of the atoms in the ground state, n0 squared, or the variance of atoms, which is this number squared. But now let's go to higher order moments. And by the way, the fluctuations and the statistical mechanics is not given correctly by the system of a Gaussian ensemble, as you might expect. Well, I'm straying from my punchline here. We can calculate now all of the higher order moments, and we find then that for the interacting gas and the ideal gas expressions, which are more or less the same, but I remind you that this is essentially phenomenological. Nothing wrong with phenomenology as long as you keep in your mind's eye that that's what you've done. We've fixed the equations of motion in a way that gives us a nice way to extend these results of CNB3 through to the critical point, which is where things are interesting at this point. Now, let me conclude by saying, okay, what about applying these master equation techniques from the very beginning? Don't use a phenomenological coupling as we did in the previous few graphs, but instead develop models for the scattering of atoms off the wall, okay? So we're thinking then of an atom coming in, hitting the wall, and emitting a phonon, scattering in a way that we discussed in the few graphs ago. Okay, now we can think of various models. There are other ways to discuss this wall interaction. I'll come back to that. But much of what we do is in this FISREV article, 2010. So Anatoly and me back 20 years ago went through this analysis. And what I thought was most interesting is this. Suppose I develop an equation of motion for this analysis of the wall system, okay, this picture, essentially the extension of our CNB1 and 2. Well, first thing I get is coupling along the diagonal. But unlike CNB1 and 2, which have only off-diagonal elements coupled along the diagonal, now we find coupling which looks like this. And that's what you get if you're studying squeezed light. Now we're beginning to make contact with what we do for a living today, both from the point of view of squeezed light and from the point of view of entangled quantum systems. This A parameter is a gain-loss parameter. The B parameter is a coupling parameter involving these Bogolubov coefficients. And we published that back 2006, volume 53 of something called the Journal for Modern Optics. I gave this talk at our Physics of Quantum Electronics conference back 20 years ago. And we were publishing papers then in this journal, which no longer exists. It became something like the Quantum Optics Journal, I think. But in any case, you find something very interesting. You find a coupling which is completely different for the two different models. So for those of you who are cognoscenti in the business of superconductivity and drift type scattering, versus what I'll call here Bose-Einstein laser atom type scattering. And you get different answers. If I go this way, I get off-diagonal coupling like squeezing. If I go this way, and this is defined in, this way is defined in this paper here, I get only diagonal coupling. So this works better. But the reason that we publish it is simply that it works, not that we have understood it. The momentum is transferred to the wall in a subtle way. And that's what I'd like to encourage people to think about. Now that we have these experiments on fluctuations in Bose condensates, let's go back and rethink some of these subtle issues associated with the Bogolubov treatment of the Bose condensate. Well, I'm over time now. Next lecture, we'll see that these ideas of the quantum theory of the laser and the Bose condensate are coming up again in the study of radiation from black holes. And that application of Bogolubov formalism will be the subject of tomorrow's lecture. And today, I indicated here that this last view graph is not the end, but hopefully the beginning of the subject. Thank you for your attention.
Oh, yeah. You all hear me? Yes?
Yeah,
So,
good.
do we have any questions from the audience? Yeah, Professor Vanderlei.
Okay, thank you, Scully, for the nice lecture. And it's very nice to see that we can import all the understanding of laser theory and fluctuation to the BC. Now, what can you say about the formation of the condensate? Because I know there are a lot of understanding about how a laser is formed, how many photons accumulate in a single mode. What can you say for the formation of the condensate?
Very, very good. Note in particular that this equation of motion for the statistical distribution of atoms in the condensate, therefore say for the variance, has two contributions. So we can solve for the time dependence analytically and even including off-diagonal coupling of this hybrid variety, strange variety. But certainly with the computer, we can get the time dependence of the atom's statistical distribution and follow the variance. So these equations are the way that we would approach that question. And we have now only the need to work that hard. It's not a simple problem. And already at this level, there are interesting new features. At what level? At the level of looking at steady state equations, putting this equal to zero. But now, encouraged by you, we'll go back and do the time dependence. And indeed, that's a good comment. Thank you.
Okay, do we have any other question? Yes? No? So Professor Scully, I have also a question. So you showed at the very end of your talk the graph of the BC fraction as a function of temperature. And you showed the curves for an ideal gas and interacting one. And I was wondering if there is an intuitive vision why the interacting case grows faster than the ideal case.
Yeah.
Because at
Isn't that
t equals
interesting?
0, it's the opposite, right? We
Right,
have a quantum depletion that for the interacting case, but at the intermediate range of temperatures, for me this is funny. I have never seen this.
Yeah. So let's take your question a step at a time.
Yeah.
So the first thing I'd like to point out is that this business of the fluctuations being a factor of 2 different in the condensate is in itself already something surprising. And big heroes like Pedievsky saw that and thought, oh, it must just be a coincidence, but it's not. And now we go back over here and we say, well, it's likewise not obvious why I should have a stiffer condensate. Why should I have more atoms, let alone the time dependence? The steady state result itself is already intriguingly surprising. I have fewer atoms in the condensate at t equals 0 because some of the atoms are being kicked upstairs by atom-atom interactions. But then when I go a little bit higher temperature, now atomic interactions, you might say, give me more coupling to the thermal reservoir and to other bosons. And so one can begin to make up stories for why this intriguing coupling gives us this intriguing result. Why does coupling give us a stronger interaction? But I think the way I want to apply it is, why are these different models for the wall giving me such remarkably different equations of motion? So as a theoretical physicist, that's the thing that I can get a handle on most quickly. Same question. What you're thinking, I think, can be addressed here. I don't know the answer, but I'm making up stories. And by the way, this was 20 years ago we did this stuff. I haven't thought about it for a long time, except that whenever I start seeing these Bogolubov problems in black hole physics, and of course we see it all the time, entanglement and the Unruh radiation, it's all, from one point of view, Bogolubov. So, but I hadn't thought about the connection the way I was encouraged to begin thinking about it, given this beautiful conference. And I have a position here for a postdoc or a graduate student who would like to work on this problem.
Okay, thank you, Scully. Do we have another question? Last one? No? So in that case, let's thank Professor Scully again, and we meet again tomorrow.
Bye-bye.
Bye, thank you.